So class, welcome to the lecture number 18th of the course Electrical Machines. So first, we are familiar with the concept of transformer, how transformer works. What is step up, step down transformer? What is the you know about the construction of the transformer, that core, primary, secondary winding, and you know the losses that are occurring in the transformer, copper losses as well as core losses. You studied about the different types of testing of a transformer. Then we solved the problems on efficiency as well as voltage regulation of the transformer. Okay. So next, let us study one special type of transformer which is commonly used in our laboratories for various experimentations. It is used in power system. It is used in electrical machines lab as well while you are doing these tests, short circuit and open circuit test. So this type of transformer is called as auto transformer. Auto transformer. So how is this auto transformer different from the conventional transformer we studied? In a normal transformer, what we have two types of windings, primary and a secondary winding. Okay. So depending upon the number of turns, so this is N1 and N2. So depending upon the number of turns, it can be a step up or a step down transformer. Since here the N2 is less than N1, so I am saying it is a step down transformer. So this is a simple transformer. However, in case of in this case means simple two winding transformer. This is a two winding transformer. You can see that both the primary and the secondary windings, they are electrically isolated from each other. Okay. So the difference between the this common two winding transformer or conventional transformer and this auto transformer is that in case of an auto transformer is a transformer in which part of the winding is common to both primary and the secondary circuit. So means that I have a winding here. Okay. So this is my primary circuit and I have a winding here. So the some part of this winding, it is common to both primary and the secondary circuit. So I can say that it is like this. So this is primary circuit and this is secondary circuit. So you can see here that the two windings, primary and the secondary windings, they are not electrically isolated from each other. So this is V1. Here the output will be here V2. Okay, current here will be I1 and the current here will be I2. So you can see that I have a winding here AB. So this winding, the primary winding is AB and the secondary winding, I am labeling a point here, secondary winding will be BC. Okay, so I am saying an auto transformer is a transformer in which a part of the winding is common to both primary as well as secondary circuit. Okay. In case of a auto transformer, the two windings are not electrically isolated from each other. Rather, a section of the same winding acts as the secondary. So which section of this winding AB it is acting as a secondary? The winding section C and B, it is acting as a secondary winding. So you got it. What is auto transformer? I am saying it is a transformer in which a part of the winding is common to both the primary and the secondary circuit. And in case of an auto transformer, there is no electrical isolation between the primary and the secondary winding. Rather, a part of the winding, it acts as a secondary winding. Okay. So next, what is the construction? Come to the construction of an auto transformer. So firstly, the most important part of any transformer, it is core. Okay, so the core of an auto transformer, it may be a rectangular core or it can be a circular ring type core. Okay, so this is a rectangular core. Okay, so you can place winding either on any one limb of the core or on both the limbs of the core. So this is primary, the secondary will be like, this is primary winding and the secondary winding will be like from here. Okay, so if this is V1, this will be V2. So this is a rectangular type core, or it can be a circular ring type core. This is rectangular. Okay, so I am saying in this case, and this is circular. Let me draw circular ring type core as well here. So this is rectangular ring type. So these are the laminations which I am drawing here. Okay, so here it will be like this. These are the laminations. So the wire will be connection, winding will be like this here. So it will be like this, like this, like this, like this, like this, like this, and it will be like this here, like this, like this, like this, this, and here I will get another terminal. So this is terminal A, this is terminal B. Okay, and here the input is V1. Okay, I am saying it can have a rectangular core or a circular disc type ring type core. No, a single winding is wound around one or two limbs. Here I am showing only one or winding on one limb. I am saying a single winding is wound on one or two limbs of a rectangular core, or it is wound around the circular ring type core. Okay, so now I will again redraw the diagrams here below. The diagrams will be like this. So the diagrams will be like this. Let me draw it first here. It will be like this. So this will be, here I will give some supply voltage V1, the current is I1, this is A, this is B, this point is C, and here I will have load. Here the voltage is V2 and the current that is flowing, it is I2. So this is a step down type core. Okay, now let me show the same diagram for this circular type. So firstly we will draw the winding which is in a circular shape, and then I will draw the rest of the circuit. So the winding will be like this. Okay, so this is my point. Here I'm giving supply, and this is my another point here. So I'm saying this is my supply, this is my point A, this is my point B. So I'm saying that I have a slider here somewhere, so it is here. Okay, so the it is going like this, and this point B is common to both the windings. So here it is A, B, this is point C. Okay, and this here I will have some load. Okay, so what is the number of turns between this in this? So I'm saying it is suppose that number of turns from this point to this point, from A to B, it is N1. Okay, and the number of turns from C to this point to B, okay, from here to here, it is N2. Got it? So this since I am saying that N1 is greater than, if N1 is greater than N2, it is step down, and if N2 is greater than N1, it is step up. Okay, so I am saying that in this figure I am showing that the terminal B here and terminal B here, it is common, means it is a common point from which one terminal of both the primary and the secondary. I am saying point B is a common point from which one terminal of primary and one terminal of secondary, they are taken out. Okay, you can see point B. So one terminal of, this is the one terminal of primary, and this is the another terminal of, and this is the one terminal of secondary. This is the another terminal of primary, and this is also the another terminal of primary. So this point B, it is a common point. Okay, and it is the one, it is the one terminal of both primary and the secondary winding are taken out from this point B. Okay, the number of turns in winding AB, they are taken as N1 from here to here, N1, and the number of turns in the winding BC, it is taken as N2. So turns from here to here, N1, turns from here to here, N2, turns from here to here, N1, turns from this point to this point, N2. Okay, so thus I am saying one section of the same winding acts as the primary, and the another section of the same winding acts as the secondary. So one section of the same winding is A to B, it is acting as the primary, and the another section of the same winding, that is B to C, it is acting as the secondary. Same is the case here. A to B primary, this is point B, A to B primary, and B to C secondary. Okay. So when the number of turns on the secondary side is less than the number of turns on the primary side, the auto transformer works as a step down transformer. Here N2 is less than N1, so I am saying it is a step down transformer. Here also N2 is less than N1, so it is a step down transformer, auto transformer. Got it? So let me draw the diagram again, this diagram again on the next page, because I want to explain the working of the auto transformer. So working of the auto transformer is almost similar to the working of the normal transformer. Okay, so I'm saying that I have a transformer here. So here I have a source voltage. So here the voltage is equal to V1. The current here is I1. So number of turns here, it is N1. So I will take a point. This is A point, this is B point, and I'm taking this as a point C point. Okay. So this is my load L. The current here is I2. The voltage here is V2. The number of turns here are N1 minus N2 in section AC. The number of turns are N1 minus N2. So the number of turns on section BC, it will be N2. Okay, got it? I will redraw this diagram again. Okay, so that you can understand it better. So tell me, so this is the main diagram. So I will redraw this diagram below to explain the working properly. So it is like this. So this is N1 turns from here to here. I have N1 number of turns. There is a switch. This is switch, this is open. Okay, this is switch as this is initially open, so this is load. Okay, so I have N1 turns here. So tell me, initially the switch is open. If the switch is open, means it is on no load. The auto transformer is on no load. Got it? Initially when the switch is open, so no current is flowing in the secondary, and the circuit transformer is on no load. And if the primary is excited by a source voltage of magnitude V1, and exciting current will flow through the primary winding, but full primary winding means from A to B. Since the secondary is open and primary is excited by a voltage V1, so current will flow through the full winding from A to point B. Got it? So if it will flow from A to point B, and the voltage applied across this winding right now, it will be V1. So can you give me the voltage per turn in the winding AB? Voltage per turn in AB, it will be given by formula V1 by N1. So this is the voltage per turn in the winding AB. So if the can you give me the voltage in segment BC? What will the voltage in the segment BC? So since the voltage per turn is V1 upon N1, so the voltage in the segment BC, it will become V1 upon N1, which is the voltage per turn multiplied by the number of turns on this segment BC. So it will be V1 divided by N1 multiplied by N2. Okay, again I will draw the same diagram to make things easier to understand. I think I should draw it here. First let me draw core. Again the switch is open here, and then I will connect a load. Okay, this is here V1. Okay, so I am telling you that when the switch is initially open, okay, the voltage and voltage V1 is applied across the primary, so exciting current will flow in the secondary in this winding in a direction this. Okay, in a direction this is A, this is C, this is B. Got it? So it will flow in a direction like this, and it will establish an MMF which will flow in the upward direction, simply in case of a transformer. Okay, so it will flow in the upward direction. Got it? Okay, MMF which is directly upwards. So when the switch this S is closed, when this switch S is closed, the moment this is closed, a current I2, okay, the current I2 in the winding, the current some I2 flows in the winding BC. So the direction of the current in the winding BC, it should be such that it should produce a flux which should oppose this flux, the initial flux, main flux. So how is it possible? How is it possible? It is only possible if the current flows means that the current I2 should produce a flux which should oppose the flux this. This flux means the flux should be downwards. Okay, for that the direction of the current should be in this direction, this I2 current direction. So if the current direction of the current is in this direction, okay, then only the flux that is produced by the current 2, it will be in the downward direction. It is simply Lenz's law, nothing else, nothing new. Okay, so you can see that in if the switch is initially open, the direction of the current I1, it is like this. Exciting current is like this, but the moment the switch is closed, the current I2 will flow in this direction through the load, and it will flow in the winding in such a direction that it will oppose this flux, main flux. Means that the flux produced by I2, it should be in the downward direction, and the direction of the current I2, it will be in this direction, in these windings from B to C. Okay, so since we are saying that transformer is a constant flux machine, so in order to maintain the flux constant, the transformer will draw additional current I1 from the circuit. Okay, it will draw additional current I1 from the circuit or from the source in order to neutralize the effect of the or neutralize the MMF that is produced by the current I2 in the winding BC. Are you getting it? So an additional current is drawn by the transformer from the source, so that the effect of this current I2, that is the flux this I2 current is producing in the winding BC, it is neutralized. Hope you got it. So I will move further now. So I'm saying when the switch S is closed, the current I2 starts flowing through the load, and the current I1 is drawn from the source. Okay, since neglecting the losses, I can say that the input power is equal to the output power. Input power is V1 I1 cos phi 1, and the output power is V2 I2 cos phi 2. Okay, since I am saying that the internal impedance drops and losses are neglected, if the internal impedance drops, that is a drop in the transformer impedance on the primary and the secondary sides, it is neglected, and the losses are also neglected, that I can say that cos phi 1 is equal to cos phi 2, and hence V1 I1 will be equal to V2 I2, or V2 upon V1 will be equal to I1 upon I2, which is equal to N2 upon N1, which is equal to K. Okay, which is simply the transformer action. Okay, nothing else. And in this circuit, which I have drawn here. In this circuit, since you know that the secondary turns are lesser than the primary turns, so obviously the N2 is less than N1, so K will be greater than, or K will be less than unity. Okay, so obviously K will be, for a step down transform, K is less than unity. Got it? So next, now I am saying that additional current I1 is drawn from the source so that it neutralizes the effect of the current that is flowing in the winding BC, so that the flux that is produced by the current in the winding BC, it is neutralized. Okay, so that the flux in the machine, it remains constant. So I can say here that the current in the winding AB, I1 flows in the winding AB, okay, from A to B. Current, in which direction current I1 is flowing? I1 is flowing in the winding from A to B. Okay, while in the winding BC, the current I2 is flowing from B to C. I2 is flowing from B to C. Therefore, the current in the winding BC is I1. Are you getting what I am saying? I am trying to say, I am saying the current in the winding AB, that is I1 current, it is flowing from A to B, and the current I2 in the winding BC, it is flowing from B to C. Okay, so since I can say that from this point to this point, I1 is flowing in this direction, and from this point to this point, I2 is flowing in this direction. In this part BC, I'm only talking about the BC part. Okay, so the two currents are flowing in the opposite direction, and since the transformer is a step down transformer, I2 will be greater than I1, then I can say that net current that is flowing in the BC is equal to I2 minus I1. Okay, this is IBC. This is the current IBC. What I am saying, that again I will write it here, again I will show it here. A, B, C, I1, this is I2, and I have a load here. Got it? So I am saying the current that is flowing in the winding AB, the current I1 in the winding AB is flowing from A to B, and the current in the winding BC, it is flowing from B to C. Okay, so in this section, if I will talk about in this section, the current I1 in this section is flowing in this direction, and the current in this section is flowing in this, current I2 in this section is flowing in this direction, I2. Okay, and since I2 is greater than I1, so the net current in this section BC, it will be, net current will be I2 minus I1. Okay, or I can write that IBC is equal to I2 minus I1. So now MMF in winding AB, AC, from winding A to C, it is given by, in winding A to C is given by nothing but current multiplied by the number of turns. So current is I1, number of turns are N1 minus N2. So I can write it as I1 N1 minus I1 N2. Okay, but also from the transformer action, I know that I1 N1 equal to I2 N2. So substitute it here. I1 N1 is equal to I2 N2 minus I1 N2. Taking N2 common, I will get I2 minus I1. So this is the flux or MMF in the winding AC. What is I2 minus I1? I2 minus I1 is nothing but the current in the winding BC. So it is N2 into I BC. Okay, so MMF in winding AC is equal to N2 into IBC. N2 are this number of turns, and what is BC? The current that is flowing in winding BC, which is I2 minus I1. So I can say that MMF in winding AC is equal to MMF in winding BC or CB. Okay, so it is therefore seen that the transformer action can take place. I can say it is therefore seen that the transformer action can take place between winding section AC and winding section BC. Okay, what I am saying, transformer action takes place between winding AC and winding BC. Okay, in other words, I can say that the volt amperes across winding AC are transferred by transformer action to the load that is connected to winding BC. Or what I am trying to say, I am saying I can say that volt ampere across winding AC are transferred or transformed by transformer action to load which is connected across BC. Okay, now let us determine the power that is transformed in volt ampere to the output. Okay, so I am saying that the power transformed in volt ampere, it is given by nothing IAC it is capital into VAC. Okay, so this is the total volt ampere in this on the primary side. Okay, VAC into IAC, which is equal to, I can say, what is VAC? VAC is nothing but V1 minus V2. Here you can see this is VAC, this is total V1 from here to here, and this is V2 from this point to this point, it is V2. So what is voltage in this section AC? It is V1 minus V2 and the current is I1. So it will be V1 minus V2 and IAC is nothing but I1. So total power input to the transformer is, or input power in volt ampere, it is given by V1 into I1. Okay. So next I will take the ratio of the two power transformed in volt ampere divided by input power in volt ampere. It will be given by V1 minus V2 into I1 divided by V1 into V1 into I1. So solve it further. I will write it at I1 will cancel, 1 minus V2 by V1. So it is equal to 1 minus K, because V2 by V1 is nothing but K. So I can say that the power transformed is equal to 1 minus K times the input power. Okay, the power that is transformed via transformer action is nothing but 1 minus K times the input power. Okay, so output in volt amperes V1 I1, where is the diagram? So I am saying the output in the volt amperes V1 out of the I can say that from this equation I can say that out of the this total input power, which is nothing but V1 I1, I am saying out of the total input power, only this much power is transferred to the output by transformer action. What I am trying to say, I am saying that out of the input volt ampere, input volt ampere is given by V1 I1. Out of the input volt amperes, only IAC VAC, okay, it is transformed by the transformer action to the output. Out of the input volt ampere, which is nothing but V1 I1, only VAC into IAC, which is nothing but V1 minus V2 into I1. Okay, so out of the total input volt ampere, which is V1 I1, only VAC into IAC, which is equal to V1 minus V2 into I1, is transformed to load or output by transformer action. ओके, अब इतना ट्रांसफार्मर एक्शन से हुआ, ठीक है, इतने में से इतना पावर जो ट्रांसफर हुआ लोड को, वो ट्रांसफार्मर एक्शन से हुआ. सो रेस्ट ऑफ द पावर इट विल बी ट्रांसफर्ड टू द लोड while means conductively. Okay, this is inductively transformer action, and the rest of the power it will be transferred conductively, means through conduction. So thus I can say, thus remaining volt ampere required to the load are conducted directly to secondary from the primary, from secondary from primary. So I am saying that suppose input is x, okay, so this x is to be transferred to the output. So I am saying out of this x1 is transferred through transformer action. X is nothing but V1 I1. So x1 is transferred through transformer action to the output, means it is V1 minus V2 into I1. So the remaining power it is transferred out of x1 is transferred via transformer action, and the remaining power is transferred to the load directly by conduction. Okay, directly by conduction. So let us determine how much power is transferred to the load by conduction. So power by conduction, it will be given by the input minus power by induction. I can write it here. So power conducted in VA is equal to total input minus power transformed in VA by transformer action. So total input power is V1 I1, power transformed in VA by transformer action. It is given by the formula 1 minus K into input power, or it is given by V1 minus V2 into I1. So I will write that formula. So it is given by V1 minus V2 into I1. So further writing it, V1 I1 minus V1 I1 plus V2 I2. So this will cancel. So I am saying that a power that is conducted directly to the output is given by V2 I2, means V2 I2 means through this part. Okay, so through this part, this is V2, this is I2. Okay, this voltage into the current that is flowing through the load. So this is the power that is given to the load directly by conduction, and the power that is given to the load by induction, it is given by V1 minus V2 into I1. Okay, so since we know the power that is conducted directly and we know the power that is transformed using transformer action, so I can say that the power conducted divided by input power conducted is V2 I2, and the input power is V1 I1. Okay, so V2 I2 is equal, if you will see the formula here I have shown, V1 I1 is equal to V2 I2. Okay, you can see this formula here, V1 I1, or I can say V2, was it V2 I1 sorry, I made a mistake, that's why I got confused. So it is V1 I1 plus V2 I1. Okay, V2 I1 divided by V1 I1. So I1 will get cancelled, so it will be 2 by V1, and V2 by V1 is nothing but equal to the K, which is transformation ratio, so which is equal to K, or I can say power conducted is equal to K times the input power. Okay, so hence I can say that power transformed power, this is conducted power, another was transformed power. Transformed power divided by input power, it was equal to 1 minus K. Transformed power means which is transferred through transformer action. Next is power conducted by input power is equal to K. So considering the equation, I can say power transformed divided by input power is equal to 1 minus K, which I further can write as 1 minus K V2 by V1 is equal to V1 minus V2 by V1. Okay, so I can say that the that power that is transformed through transformer action, which is nothing but the inductive action. Okay, I can write it as further it as inductively transformed power divided by input power is equal to V1 minus V2 by V1, which is nothing but higher voltage minus lower voltage divided by higher voltage. Got it? So I told you that in an auto transformer we can power transfer is power this inductively or through transformer action in the winding AC, because of the winding AC, and because of the winding and the remaining power that is to be given to the load, it is transferred conductively. So we have conductively transferred power and we have inductively transferred power, and the total power is nothing but a summation of the two power. Okay, so next let us discuss about something which is very important for auto transformer. Means one of the great advantage of auto transformer is that copper material is saved. In case of an auto transformer. So we say that if the copper material is saved, that means for first I would like to say means how much copper we have to use, or I'm saying that volume or weight of the copper, it depends on which factors. I'm saying the volume and weight of copper. Okay, volume of the and weight of the copper which is to be used is proportional to the length and area of cross section of the conductor. Area of क्रॉस सेक्शन ऑफ कंडक्टर. लेंथ मीन्स कितने टर्न्स हमने यूज करने हैं, and area of cross section of the conductor means how thick the conductor is. So now length of the conductor, I am saying length of the conductor, it is proportional to the number of turns, and area of the cross section of the conductor, okay, is proportional to the current that is flowing through it. Okay, so next, hence I can say that the weight of the conductor is proportional to the product of the current and the number of turns. Okay, because number of turns will determine the length and the current will determine the area of the cross section, and the both length and area of cross section, they will determine the weight of the copper that is used. Okay, so that is why I am saying that length of the conductor is proportional, that's why I am saying that weight of the copper is proportional to the product of the number of turns and the current. Okay, so now with reference I will make two figures first. One is an auto transformer and another one will be a normal transformer. So first let me draw a figure for it. So this is my auto transformer and this is auto transformer V1. Here the voltage is V1. Number of turns here are N1. Here the number of turns are N2. The current here is I1, the current here is I2, and in this section the current is I2 minus I1. Okay, and here the voltage is V2. I have a load here. Got it? So in this transformer you can see let us determine the weight of the auto transformer. Here it depends on what I am saying, that weight of the auto transformer, it depends upon the weight of the copper in the winding AC and the weight of the copper in the winding BC. Weight of copper in section AC plus weight of copper in section BC or CB. So weight of the copper in section AC, it will depend upon the number of turns in the section AC and the current that is flowing in the section AC. So I am saying that it is proportional to this thing, it is proportional to I1 into N1 minus N2. Now the weight of the copper in the section BC, okay, plus weight of the copper, it is proportional to I2 minus I1 into N2. So solving this further, I will say that it is proportional to weight of the auto transformer is I1 N1 minus I1 N2 plus I2 N2 minus I1 N2, or I can say it is I1 N1 plus I2 N2 minus twice I1 N2. Okay, I am saying that the weight of the auto transformer is proportional to these equation. So let us determine the weight of the weight of the two winding transformer of the same capacity. Okay, of the same capacity. ठीक है ना? So for that I will say that I will have windings like this. This is my primary, and then I have a core here, iron core here, and then I will have the secondary. So here I have load. This is N2, this is I2, this is V2, this is I1 N1, and the voltage here is V1. Now I am saying that in an ordinary two winding transformer, so I am saying the duty means now this transformer will perform the same duty as that is performed by this transformer. Auto transformer means it will handle the same power, it has the same capacity as this one. Sorry, not capacity, means same duty. जो इसका होगा वही इसका होगा, ठीक है ना. So the total weight of the copper required in ordinary transformer, it is given by weight of this in ordinary. This is WTA in auto transformer and WTO in ordinary transformer. It is nothing but weight of primary winding plus weight of copper in primary winding, weight of copper in secondary winding. Okay, so weight of the copper in the primary winding, it is I1 N1, and weight of the copper in the secondary winding, it is I2 N2. Okay, so now take the ratio of the weight of the copper material in both the transformers. So I will see that this WTA divided by WTO. So it was I1 N1 plus I2 N2 minus twice I1 N2, and WTO was given by I1 N1 plus I2 N2. So if I will solve this, like I will simplify this equation like I1 N1 plus I2 N2 divided by I1 N1 plus I2 N2 minus twice I1 N2 divided by I1 N1 plus I2 N2. So it will give me here 1 minus twice I1 N2 divided by I1 N1 plus I2 N2. So what I will do here in this, multiply this numerator, divide numerator and denominator by I1 N1. Okay, divide numerator and denominator by I1 N1. So it will be 1 multiplied 1 by I1 N1, multiply and divide, multiply by it by I1 N1, and then divided by I1 N1, it will be 1. So minus on this term, multiply the numerator and denominator by, divide the numerator and denominator by I1 N1. So here it will be twice I1 N2 divided by I1 N1 divided by I1 N1 divided by it is I1 N1 divided by I1 N1 plus I2 N2 divided by I1 N1. So if you will, what I am doing, I am dividing numerator and denominator by I1 N1. Okay, so it will give me the same expression, this expression. Okay, but I am doing this to make the things simpler. Okay, to represent this complex equation in terms of a simple equation. So if you will see, it will be I1 N1, I1 N1 will cancel out each other. It is I2 N2 divided by I1 N1. This is I2 N2 divided by I1 N1. So if I will simplify this formula, I will get somehow that this ratio is going 1 minus, where is my k? I have derived a formula for k somewhere. Okay, yes, k is nothing but, where is the formula? Okay, so if I will take this method, I will say V1, this I1 by I2 is equal to N2 by N1 is equal to K. So if you will use this thing here, this thing here, this thing here, you will get this term as K. Okay, so this term 1 minus K. If you will, you try it at your own places, means substitute this I1 N1 is equal to I2 N2. From here you will get I1 N1. If you will solve it, you will get I1 N1 is equal to I2 N2. So I1 N1 is equal to I2 N2. So it will be, is 1. They both are equal. So here it is 1. So I1 N1 is equal to I2 N2. So this is I1, but it is coming a bit different here. So in the denominator I will get 2 divided by 2 I1 and 2 divided by I1 N1. Okay, I1 and 2 divided by I1 N1. So I will cancel each other, right? I am 1 minus 2 will cancel, so it will be N2 by N1. So N2 by N1 is nothing but 1 minus K. N2 by N1 is K. So you got that weight of the auto transformer divided by weight of the ordinary transformer is equal to 1 minus K. I can write weight of the auto transformer is equal to 1 minus K times the weight of the ordinary transformer. So saving of copper material, that is the saving of the copper material, it is affected by the use of the auto transformer. Okay, so I can say that the weight of the auto transformer is equal to weight of the ordinary transformer, okay, minus weight of the, so let us say you got the weight of the auto transformer, okay, in terms of the weight of the ordinary transformer. So can you say how much copper material is saved? How much copper material is saved in when we are using an auto transformer instead of an ordinary transformer? So saving in copper material is given by, is equal to weight of the copper required in ordinary transformer minus weight of the copper required in auto transformer. So it is WTO minus 1 minus K times WTO. So it is WTO minus WTO plus K times WTO. Okay, so saving is given by saving of copper material is nothing but K times the weight of the material that is required in the two winding transformer or ordinary transformer. So you know how much, you see how much copper you have saved. Okay, since you are saying that you have saved the copper, so it has certain advantages. It has certain advantages. Saving the copper material will give you certain advantages. What are the advantages? Advantages of ordinary transformer, means auto transformer over two winding or ordinary transformer. Number one is the quality of the conductor material is less. Quantity of conductor material required is less, means less quantity of conductor material is required. So we know that the quantity of the conductor material required for an auto transformer having the same rating as the ordinary two winding transformer is only 1 minus K times, okay, which we derived. Okay, So because of this saving in the conductor material, huge investment cost is reduced. Number second, quantity of magnetic material required is less. Magnetic material is required is less. Why quantity of magnetic material that is required means that means core material it is less, because you during designing the window of the transformer, during designing the windows of the transformer, okay, during designing the windows of the transformer, the window dimensions are decided from the consideration of insulation and conductor material. ओके मीन्स हमारा कंडक्टर मटेरियल कितना, अगर ज़्यादा है तो हमें बड़ा विंडो रखना है, ठीक है ना. सो आई एम सेइंग the window dimensions are decided from the consideration of insulation and conductor material. So for an auto transformer, a reduction in the conductor material means lower window area, and therefore smaller core lengths are required. Okay, reduction in copper material means lower window area, and lower area means smaller dimensions. A window of smaller dimensions are required. Okay, it shows that for the same core area, the weight of the auto transformer core is less. Okay, for the same, I'm saying that it shows that for the same core area, the weight of the auto transformer core is less, hence further there is further saving in the core material. Okay, so I'm saying that auto transformers are more economical than the two winding transformer. Okay, so next I am saying third, it operates at higher efficiency. It operates at higher efficiency. How? Since I am saying that the quantity of the conductor material it reduces, okay, and the quantity of the conductor material reduces, the this core dimension it will also reduce, and the core material required it will also reduce. Since the reduction in the conductor material means reduction in the copper loss, and reduction in the core material means reduction in the core loss or iron loss. So if the losses will reduce, then the efficiency will increase. That is why we are saying that it operates at higher efficiency. Fourth, it operates at better voltage regulation. It operates at better voltage this regulation. I am saying that the reduction in the conductor material means lower value of ohmic resistance. If conductor material that is copper required is requirement of copper it reduces, that means ohmic resistance will reduce. Ohmic resistance reduces. Okay, a part of the winding, because this time that the part of the winding is common. Okay, so leakage flux will reduce. I'm saying in an auto transformer we have some part of the winding, it is common to both the primary and the secondary, so there is no leakage flux, so leakage flux will reduce. If the leakage flux will reduce, so leakage reactance XL0 it will reduce. So in other words, if ohmic resistance and leakage reactance both will reduce, the impedance of winding or transformer will reduce. Winding reduces, because impedance will depend upon nothing but R and X. If both will reduce, then impedance will reduce. If the impedance will reduce, that means the drop in this impedance it will reduce. If the drop will reduce, means we will get better voltage regulation. Got it? So these are the advantages. So there are some disadvantages of there are 4 advantages, and there are few disadvantages of the auto transformer as well. So though we say that the auto transformer it is less costly, it has better voltage regulation, and it has lower losses as compared to the ordinary transformer. Okay, so which I showed you why, but voltage regulation is better because impedance reduces. Why? It has lower losses because conductor material and copper losses, this core material it reduces. Okay, that is why I am saying that auto transformer has less cost, better voltage regulation, lower losses as compared to the ordinary 2 winding transformer, but still it has some disadvantages. One major disadvantage, and that is that the secondary winding is not insulated from the primary. You can see that a secondary winding it is not insulated from the primary. So if an auto transformer is used to supply low voltage Okay, from a high voltage. This is a high voltage, this is a low voltage. So I am saying if a auto transformer is used to supply low voltage from a high voltage, and there is a break in secondary winding. So if there is a break in the secondary winding, then the full primary voltage comes across the secondary terminals. Okay, full primary voltage will come across the secondary terminals, which may be dangerous to the operator and equipment, that a load, that means the load which is connected. So what I am saying, I am saying that if the auto transformer is used to supply the low voltage from the high voltage, and there is break in the secondary winding, then full primary voltage will appear across the secondary or across the load. Okay, since I'm saying there is open circuit, break here means it is open circuit, so whatever is the voltage here, same voltage will appear across the load. Okay, so if this high voltage will appear across the load, it will be dangerous for the operator who is handling the auto transformer, or it may be dangerous for the load which is being supplied from this auto transformer. Okay, so therefore it is advisable not to use this auto transformer for interconnecting the high voltage and low voltage system. Okay, and the use of this auto transformer, it is only limited to the places, it is only limited to places where slight variation of output voltage from the input voltage is required. Okay, where very slight variation of output voltage from the input voltage is required. At that point, in those applications, we use this auto transformer. Got it? So I think I should stop here. Okay, so in the next lecture we will study about this comparison between the auto transformer and a two winding transformer. Thank you very much.